Hello friend, welcome to this lecture. In this lecture we will discuss about Duhamel principle and its application. Now Duhamel principle is very important concept, and it will help us to find out the solution of non-homogeneous equation with the help of homogeneous equation. So basically for example, you have this kind of problem, say utt equal to k u x x plus f of x t and u of say x 0 equal to say f of x, ut of x 0 equal to g of x. So consider this as a one dimensional wave equation, and here x is lying between say minus infinity to infinity and t is greater than 0, and at t equal to 0 we have these initial condition. Now we know the solution when this forcing term f of x t is not there. So it means that we know the solution of utt plus k u x x, u x 0 equal to f of x, ut x 0 equal to g of x. But if we put any kind of force here, that is f of x t, then we do not know how to find out a solution. Of course there are certain method available, but here we will discuss a method of solution solving this non-homogeneous problem with the help of say homogeneous problem, that is k u x x. So here let us say w, and here we have w x 0 equal to say f of x, w t of x 0 equal to g of x, and how we can relate the solution of this non-homogeneous problem as a solution of this homogeneous problem. That is the thing we wanted to discuss here. So let us proceed. So let the Euclidean 3-dimensional space be denoted by R3. So here we just taken started with R3. You can work in R2 or R. The same concept will work, and a point in R3 be represented by capital X equal to x1, x2, x3, and if v x t tau satisfy for each fixed tau the PD v t t x tau minus c square del square v x t equal to 0, x belongs to R3 and t is greater than equal to tau, with the condition that v x tau tau equal to 0 and v t x tau tau is equal to f of x tau. So once we know the solution of this, where f of x tau denote a continuous function defined for x in R3, and if u satisfy u x t equal to 0 to t v x t tau d tau, then this is the important thing, then this u which is defined like this satisfy the the non-homogeneous equation given as utt minus c square del square u equal to f x t, x belongs to R3, t greater than 0, u x 0 equal to 0 and ut x 0 equal to 0. So it means that here if you look at this is what, this is a non-homogeneous equation utt minus c square del square u equal to f x t. This is a non-homogeneous equation with homogeneous initial condition. The solution of this we are finding by the solution homogeneous equation with non-homogeneous initial condition. So relation between these two problems is given by this relation, that u x t can be given as 0 to t v x t tau d tau. So here we are not giving the exact proof of this result, but we will verify that if u x t is given as 0 to t v x t tau d tau, where v x t tau is a solution of this problem, then u x t will be solution of this problem. The original the actual proof involves a lot of say concept involving this Laplace transform, so which we are not going to give in this lecture, rather than we are just showing that if we define u x t like this, then it will satisfy this non-homogeneous equation with homogeneous initial condition. So let us consider the equation utt minus c square del square u equal to f x t with u x 0 equal to ut x 0 equal to 0. So here we have a non-homogeneous equation and with homogeneous initial conditions are given, and assume that the solution of the problem is of the form u x t equal to 0 to t v x t minus tau tau d tau, where Vxt minus tau tau is a one parameter family solution of this Vtt minus c square del square u equal to 0 for all t greater than equal to 0, and for at t equal to tau Vx0 tau equal to 0 for all values of tau, and Vt x 0 tau is given as f of x tau. Please look at here, if you look at the statement of the result here we have assumed that Vxt tau is a solution of this problem, but here your t is greater than equal to tau. So, but we whatever so it means that here your partial differential equation start from in say arbitrary point tau, but if we make this kind of translation like t minus tau, then this the solution of this, which is given as Vxt tau, will satisfy we can write Vxt tau as V tilde x t minus tau tau, then this V tilde x t minus tau tau will satisfy the following equation V tilde t t minus c square del square V tilde equal to 0, and here your x belongs to R3 and t is greater than equal to 0, rather than starting from t greater than equal to tau. Now, for this V tilde is t is greater than equal to 0, and initial condition if we look at, then V of x, now at t equal to tau we have the initial condition 0. So, I can write, since we are assuming Vxt tau as V tilde x t minus tau tau. So, at t equal to tau this value is what, V tilde x 0 tau is given as 0, and V tilde x 0 tau is given as f of x tau here. So, it means that if Vxt is a solution of this problem, then we can say that by suitable change we can say that V tilde x t minus tau tau satisfy this problem. Is it okay? And we already know how to solve this particular problem. So, here we can say that by taking V tilde, which is a solution of this problem, we can write Vxt as V tilde x t minus tau tau. So, here we simply say that in place of writing Vxt tau, now we are writing V tilde x t minus tau tau d tau. So, here that is what we are writing in equation number 2, that Uxt is given as 0 to t Vxt minus tau tau d tau, where Vxt minus tau tau is a one parameter family solution of Vtt minus c square del square u equal to 0 for all t greater than equal to 0, and at initial condition is Vx0 tau is 0 and Vtx0 tau is fx tau. So, it is one of the same result. So, here when we define Uxt as this, then your Vxt will satisfy this equation, but and it is valid for t greater than equal to tau, and at t equal to tau initial conditions are given. But if we take Uxt as 0 to t Vxt minus tau tau d tau, then in this case this V xt minus tau tau is a solution of this equation, and it is defined at t greater than equal to 0. So, now let us verify this. So, here we have u. Now, let us differentiate this u with respect to t using Leibniz rule. So, ut is v. So, here what is that? Let me write it here. Uxt is equal to this. So, we can write ut. So, ut is equal to, so 0 to t, and then it is Vt x t minus tau tau d tau plus, and then here you put the value in place of tau you are putting value t. So, we can write it x 0 and t here, and so here what is the value of Vx0 tau? Here Vx0 t is equal to 0 for all values of tau. So, this will be cancelled out. So, we have Vt equal to 0 t Vt x t minus tau tau d tau. So, that is what it is here written, that we can write ut as Vx0 t plus 0 to t Vt x t minus tau tau d tau, and we can use initial condition, then this part is simply vanished, and we can write ut equal to 0 t Vt x t minus tau tau d tau. Now, again you differentiate with respect to t, then if you differentiate with respect to t, then you have utt equal to Vt x 0 t plus 0 t Vtt x t minus tau tau d tau. and using equation 3, the above equation is reduced to, because here we already assumed that this Vxt minus tau is a solution of Vtt minus c square del square V equal to 0 for all t greater than equal to 0. So, we can replace the value of this Vtt as c square del square u. So, that is what we have written, that is Utt equal to Vt x 0 t equal to plus 0 to t c square del square V d tau, right. And here if you remember what we have defined u x t is equal to 0 to t V x t minus tau d tau. So, if we find out u x x del square u, so del square u is defined as 0 to t del square V x t minus tau d tau, and we already know that in place of this we can write down c square del square u. That is what we have written, that utt minus c square del square u equal to Vt x 0 t, and we already know that Vt x 0 t, if you look at here, that our Vt x 0 t is Vt x 0 tau is f x tau. So, Vt x 0 t is going to be the function f x t. So, using this we can write that Vt x 0 t is your f of x t. So, we satisfy that if we satisfy this relation, that is Vtt minus c square del square u equal to 0, and Vx 0 tau is 0, Vtx 0 tau is f x tau at t equal to tau, then u defined by this, that u x t is equal to 0 to t V x t minus tau d tau, then this u will satisfy this relation, that utt minus c square del square u equal to f of x t. So, we can say that if we satisfy this equation with initial Vx 0 tau is 0 and Vtx 0 tau is equal to f x tau at t equal to tau, then you will satisfy this equation. Now, we have to look at the initial condition satisfied by u. So, let us look at your initial condition. So, here your u x 0 will be what? U x 0, you can find out that it is at put t equal to 0, then it is nothing but 0. So, u x 0 is going to be 0. Now, what about ut x 0? So, for looking at ut x 0, look at this coefficient here, and if you put t equal to 0 again, then ut x 0 is again coming out to be 0. So, here you will satisfy that if u x t is defined by this, then you satisfy this non-homogeneous partial differential equation with homogeneous initial condition, that is ut x 0 equal to 0 and u x 0 equal to 0, and this is valid for any dimensions whether it is r square or r cube. So, this is the concept given by Duhamel principle, and we are going to utilize this concept to find out solution of non-homogeneous equation, partial differential equations. So, here let us take one example of one dimension wave equation. So, consider the non-homogeneous wave equation utt minus c square u x x equal to f x t, and x is lying between minus infinity to infinity, t greater than 0, and initial condition is given that u x 0 equal to 0 and ut x 0 equal to 0 here. So, here now again question may come that when we discuss our wave equation, we have assumed our initial conditions as non-homogeneous initial condition, but here whenever we consider this kind of problem where utt equal to k u x x plus f of x t and u x 0 equal to f of x and ut x 0 equal to g of x, then we can always write this into two part. One part is that utt equal to k u x x plus f of x t, and initial condition is simply 0, and let us say that u1 satisfy this and u2 satisfy this equation, that utt equal to k u x x and u x 0 equal to f of x and ut x 0 equal to g of x. Then your original solution u, I can write this u as u1 plus u2. You can verify that if u1 satisfy this equation, this system, and u2 satisfy this system, then u1 plus u2 will satisfy this partial differential equation, non-homogeneous partial differential equation with non-homogeneous initial condition. So, and we can always solve this equation given for u2. So, you can always find out u2. So, only thing we want to solve is how to get u1. So, how to get the solution of this non-homogeneous partial differential equation with homogeneous initial condition. So, our emphasis is to solve non-homogeneous partial differential equation with homogeneous initial condition. So, that is why we are considering here a non-homogeneous wave equation with homogeneous initial condition. So, now let us consider the function v x t minus tau tau which satisfy the following equation, that is v t t minus c square v x x equal to 0 at t is greater than 0 and x is lying between minus infinity to infinity, and initial conditions are what, v x 0 tau is equal to 0 and v t x 0 tau is f of x tau. So, here this non-homogeneous forcing term is now we are taking here at a initial condition of one less order. So, here it is utt. So, it is one less order means vt I am writing as f x tau. So, our if we can find out the solution of this problem, then solution of this problem I can write it u x t is equal to 0 to t v x t minus tau tau d tau. So, that is our claim, and see how this claim is verified. So, here the solution of this problem is v x t tau equal to 1 upon 2 c x minus c t x plus c t upon into f of s tau ds. So, here the solution of this problem equation number 10 along with the initial condition 11 is given by this, that v x t tau is equal to 1 upon 2 c x minus c t to x plus c t f of s tau ds. Now, using this v x t tau, let us write down the solution u x t as 0 to t v x t minus tau tau d tau. Now, we already have the expression for v x t tau. So, we can always find out the expression for v x t minus tau. So, let us verify that this will be a solution of our non-homogeneous equation with the initial homogeneous initial conditions. So, find out ut is v x 0 tau plus 0 to t v t x t minus tau tau d tau. Now, since v x 0 tau v x 0 t is given as 0, that is what it is written here, v x 0 tau is equal to 0 at t equal to tau. So, we can say that v x 0 t is given as 0. So, we can write 0 t v t x t minus tau tau d tau. So, again differentiate one more time, then u t t equal to v t x 0 t plus 0 t v t t x t minus tau tau d tau. Now, this value v t x 0 tau v t x 0 t is again given here, v t x 0 tau is f of x tau at t equal to tau. So, v t x 0 t is your f of x t. So, using this we can write f of x t plus 0 t v t t x t minus tau tau d tau. Now, here we already know that if u is given by this, then you can find out u x x by simple differentiating with respect to x variable, and you can write u x x is equal to 0 t v x x x t minus tau tau d tau. So, we can write u t t minus c square u x x equal to u t t is having this value, that f x t plus 0 t. So, f x t plus 0 to t v t t d tau. Now, u x minus c square u x x means minus c square v x x. Now, since we satisfy this partial differential equation, so we can say that this part is gone and we have u t t minus c square u x x equal to f of x t here. And also we observe that u x t satisfy the conditions 9, that is initial condition. Look at here, condition is that u x 0 equal to 0 equal to u t x 0. So, that we can verify from this, that here if we look at the equation number 13, if we put t equal to 0, then we will get the value 0. So, this implies that u of x 0 equal to 0, and if you want to find out the value of u t x 0, then we can look at this equation and put t equal to 0, then also we are coming out to be, we are getting the value 0 here. So, it means that u satisfy the initial condition and you satisfy this non-homogeneous partial differential equation. So, if the initial data 9 is replaced by, now if we replace the initial condition by non-homogeneous initial condition, then we can, as we have pointed out, then we can write down the solution u as solution given by u1 and u2. So, what is u1? U1 is the solution of this utt minus c square uxx equal to 0 and ux0 equal to f of x, ut x0 equal to g of x. This is the u1, and u2 will be solution of this, that utt minus c square uxx equal to f of xt and u of x0 equal to 0 equal to ut x0. So, that will be the part u2, and solution u is given as u1 plus u2. So, u1 we already know the solution given by D'Alembert's wave solution, that is 1 upon 2 f of x plus ct plus f of x minus ct plus 1 upon 2 c x minus ct to x plus ct gs ds. Now, to find out this u2 is given as 0 to t vxt minus tau dou d tau. So, let us write down here our u2 is equal to 0 to t vxt minus tau d tau. Now, what is this vxt minus tau? It is the solution of what? It is the solution of this vtt minus c square vxx equal to 0 and v x0 tau is equal to 0 and vt x0 tau is equal to your f of x tau. So, here solution of this, your v x t tau is given as 1 upon 2 c x minus ct to x plus ct f of s tau d of s. That is what we have written here as equation number 12. So, once we have vxt tau, then you can find out uxt tau as, this implies that uxt is given as 0 to t, and now we are writing vxt tau. So, in place of t I am writing just t minus tau. So, here you just replace t by t minus tau. So, it is 1 upon 2 c x minus c t minus tau and x plus c t minus tau, your f of s tau ds, and then we have d tau. So, this we can write it here as this, that 1 upon 2 c 0 to t x minus c t minus tau x plus c t minus tau f of s tau ds and then d tau. So, here the this is the part u2 which we are looking at. So, u2 is written as this and u1 is already obtained as a solution D'Alembert solution of one dimension wave equation. So, that is how we find out the solution uxt of the problem, that we have a non-homogeneous problem with non-homogeneous initial condition. Now, we will move to next problem, that is solving the wave equation, but this time it is a finite domain problem, that is we are looking at finite string problem where one end is fixed at x equal to 0, another end is fixed at x equal to L. So, here we have a problem utt minus c square uxx equal to f of xt, where x is lying between 0 to L, t is greater than 0, ux0 equal to f of x, x is lying between 0 to L, utx0 equal to g of x, u0t equal to 0 and ult equal to 0. So, again we truncate into two problem u1 and u2, where u1 will satisfy what? u1 will satisfy this utt minus c square uxx equal to 0 and ux0 equal to f of x, ut x0 equal to g of x, u0t equal to 0 and ult equal to 0. So, this will contain everything other than the non-homogeneous term sitting here, and u2 will satisfy this equation utt minus c square uxx equal to f of xt and ux0 equal to 0 equal to utx0 and u0t equal to 0 equal to u of lt. Now, this we already know. Now, we want to find out u2. For finding u2, will use the Duhamel principle, and we write down this as u x t equal to 0 to t v x t minus tau tau d tau. What is v x t minus tau is a solution of, it is a solution of v t t minus c square v x x equal to 0, u v x 0 is equal to 0, and v t x 0, so let me write it tau here also because it is depending on f of x tau. So, we already know how to find out the solution using the form of u1. So, then I can find out v and then put it here, and then it will give you u2, and we can write down solution u as summation of u1 and u2. And if you look at your u part is u1 is given by this, that n equal to 1 to infinity a n cos n pi c t by L plus b n sin n pi c t by L into sin n pi x by L. So, here we have this thing. Then u2 where a n is what? A n is 2 by L 0 to L f of x sin n pi x by L dx, and b n is 2 by n pi c 0 to L g x sin n pi x by L dx. Now, if you look at u2, u2 is what? u2 will satisfy this kind of equation. So, let us find out the solution of this. So, solution is given as v x t tau is a solution of summation, here let us say c n sin n pi c t by L into sin n pi x by L. Why? Because here v x 0 tau is 0. So, we this corresponding to this cos n pi x by L will not be there. If you look at corresponding to cos n pi c t, a n will not be there because f x is 0. So, a n is going to be 0. So, we do not have any term corresponding to this. So, here we will get v x t tau as this. Now, once we have v x t tau, where c n is given as what? C n is given as 2 by L f of x tau sin n pi x by L and d of x here, right. So, c n is given by this, and 0 to L here. Then v x t tau is given by this. Then if we replace t by t minus tau and integrate between 0 to t, we will get u x t. So, that is what we have written here. It is 0 to t c n tau sin n pi c t minus tau upon L d tau into sin n pi x by L. And how to find out c n tau? C n tau is 2 by n pi c. Look at your b n, and if you look at the similarity, it is given by 2 by n pi by c 0 t f of x tau sin n pi x by L d of x. So, using the u1, you can find out the solution u2 in a similar way. The only thing is here v x t minus tau. So, if when we solve this v x t, you replace just t by t minus tau, and you can get the corresponding part of u2. So, we can write it like this. Now, coming out to heat equation. So, it means that if Duhamel principle is known, then we can find out the solution of non-homogeneous problem using Duhamel's principle. So, now let us do the same thing for heat conduction equation. So, here consider the heat equation in an infinite rod with a heat source u t equal to k u x x plus f of x t, x is lying between minus infinity to infinity and t is greater than 0, and initial condition is given that u x 0 equal to f of x, and we want to find out the solution here. So, here we again use the part that u x t can be written as integral of 0 to t v x t minus tau. So, we first find out the solution which v x t tau satisfying. So, here let us say that we have a function v x t tau satisfying this equation v t minus k v x x equal to 0, where x is lying between minus infinity to infinity and t is greater than tau greater than 0, and the following condition hold that v x t tau is equal to f of x tau. So, here if you look at here we have one derivative. So, one less derivative is 0 derivative. So, here condition v x tau tau is given as f of x tau, and we already know that the solution of this 17 and 18 is given by this. Here you simply replace by so here t is greater than or equal to tau. So, you just replace t minus tau, and we can find out this solution like Vt minus k Vxx equal to 0, and x is lying between minus infinity to infinity, t greater than 0, and Vx 0 tau is f of x tau. We already know how to solve this, and once we solve this you just replace by t minus tau, you replace t by t minus tau, and you can see that Vxt tau, which is the solution of this, is given by 1 upon 2 root pi k t minus tau minus infinity to infinity f xi tau exponential of minus x minus xi whole square divided by 4 k t minus tau d xi. So here you see that here t is replaced by t minus tau, and we already know the solution is this. So now we verify that this uxt, which is given by 0 t Vxt tau d tau, is a solution of our problem. So again you differentiate utxt, it is Vxt t plus 0 t f Vtxt tau d tau. Now Vxt is already given as fxt is equal to 0 t Vtxt tau d tau. Now we already know we can find out here uxx, and uxx is what? Uxx is 0 to t Vxx x t tau d tau. So using this we can write ut minus k uxx equal to f of xt plus 0 t Vtxt tau minus k times Vxx xt tau d tau. So this part is going to be 0 because we satisfy the heat equation, that is what we have assumed in equation number 17. So from 17 we can say that this integral part is gone, and we have ut minus k uxx equal to f of xt, and you can also verify here that at t equal to 0 ux0 is equal to 0 here. Yeah. So here we have this. So here we have ux0 equal to 0 here, but we have assumed the initial condition that ux0 equal to f of x. So here again we have to do this part, we have to use superposition of principles. So we have to write a component corresponding to the non-homogeneous initial condition, that is 1 upon 2 root pi kt from minus infinity to infinity f xi exponential of x minus xi whole square upon 4 kt d xi, plus component which we have just obtained, that is u2 here. And what is u2 here? u2 is 0 to t 1 upon 2 root pi k t minus tau minus infinity to infinity f xi tau exponential of minus x minus xi whole square upon 4 k t minus tau d xi d tau. So here when we replace our homogeneous initial condition by non-homogeneous initial condition, then we have to write our solution as u1 and u2, and u1 is here is a solution of homogeneous initial condition, that is ut minus k uxx equal to f of x t and u of x 0 equal to 0, and u2 is a solution of this ut minus k uxx equal to 0 and u of x 0 equal to f of x. And this solution we have already obtained like this, and this solution we just now obtained using Duhamel principle as 0 to t Vxt minus tau d tau. So here we have written v1 like this. So by writing u1 plus u2 you have a solution of the problem that ut minus k uxx equal to f of xt and u of x0 equal to your f of x. So here we have a non-homogeneous equation with non-homogeneous initial condition that can be written as addition of u1 and u2. Now let us look at a one more problem, that is find the solution of the following heat equation, that ut equal to k uxx plus f of xt and with initial condition ux0 equal to f of x, and this time we are taking boundary condition or also non-homogeneous boundary condition, that is u0 t equal to h1t plus and ult equal to h2t. We have also considered this kind of problem earlier also, but again I am repeating it again. So here let us assume that here first our thing is that we assume that homogeneous condition boundary condition should be homogeneous. So first we convert whenever we have this kind of problem with non-homogeneous boundary condition. So first work is to say make our boundary condition are homogeneous boundary condition. So, here let us assume that Vxt equal to Uxt plus Atx plus Bt, where At and Bt we can obtain in a way such that V0t is equal to 0 and Vlt equal to 0. So, this we can find out by writing V0t equal to 0. This implies that Bt is equal to minus H1t and Vlt equal to 0. So, this means that At is coming out to be H1t minus H2t divided by L. So, Vxt we can write it Uxt plus this Atx minus H1t. So, once we have Vxt, then we can so it means that our initial condition, if we define Vxt as Uxt plus Atx plus Bt, the boundary condition must be homogeneous. Now, look at the initial condition and the equation itself. So, here we find out the Vxx, and Vxx is coming out to be Uxx, that we can verify, and Vt we can find out Vt as Ut plus H1 dash t minus H2 dash t upon L x minus H1 dash t. So, Vt we can write it Ut plus this quantity, this thing. Now, here we already know that Ut is equal to Kuxx plus f of xt. So, using the expression for Ut, we can write Vt as Kuxx plus f of xt plus H1 dash t minus H2 dash t divided by L x minus H1 dash t. Now, this whole thing we write it a new function, that is f tilde xt. So, we can write Vt equal to Kuxx plus f tilde xt, where f tilde xt is f of xt plus this quantity. So, here our initial condition also we need to check, Vx0 equal to Ux0 plus H10 minus H20 upon L x minus H10, and we can write it here Ux0 is f of x. So, f of x plus this quantity, we call this as quantity as f tilde x. So, it means that if we use Vxt as Uxt plus Atx plus Bt to make our boundary conditions our homogeneous boundary condition, then we will satisfy this equation, that is Vt equal to Kvxx plus f tilde xt, Vx0 equal to f tilde x, V0t equal to 0 and Vlt equal to 0 here. Now, we want to solve this particular problem, then as usual we can try to solve this problem by writing in V as a addition of two function, that is V1 and V2, where V1 satisfy this problem, V1t equal to Kv1 xx, V1x0 equal to f1 tilde x, V10t equal to V1lt equal to 0. So, this is the usual problem which we have, we know how to find out the solution, but this V2 will satisfy the non-homogeneous equation with homogeneous initial condition and homogeneous boundary condition, that is V2t equal to Kv2 xx plus f tilde xt, V2x0 equal to 0, V2a0t equal to V2lt equal to 0. So, V1 we can find out like this, that n equal to 1 to infinity an exponential of minus n square pi square kt upon L square sin n pi x by L, and where an you can find out as 2 by L 0 to L f1 tilde x sin n pi x by L dx. Now, to find out V2, we look at this, we solve the following PD, that is Ut minus Uxx equal to f tilde xt and x is lying between 0 to L, t is greater than 0, U0t equal to Ult equal to 0, Ux0 equal to 0, and for this we use the Duhamel principle. For that, using Duhamel principle, the required solution is given by Uxt equal to 0 to t, Vxt minus tau d tau. Now, what is Vxt minus tau is a solution of, here we can say that Vxt minus tau is a solution of Vt minus Vxx equal to 0, x is lying between 0 to L, t greater than 0, V0 t tau equal to Vl t tau equal to 0, and Vx0 tau is f tilde x x and tau. So, for this we can find out the solution as this, that Vxt tau is equal to n equal to 1 to infinity a n e to power minus n pi by L square t sin n pi x by L, and here your an, the coefficient an you can find out as an tau as 2 by L 0 to L f tilde x tau sin n pi x by L dx. So, Vxt tau is known to us, then you can find out Uxt as 0 to t, Vxt minus tau d tau. Now, the only thing is in place of t we write t minus tau. So, we can write n equal to 1 to infinity a n tau e to power minus n pi by L square t minus tau sin n pi x by L d tau. So, in this way we can find out V2 like this, and your V1 is already given by this, then we can find out our V, and once V is known you can find out U using the relation this, that uxt is equal to vxt minus atx minus bt. So, you can solve a very general problem, that is ut equal to kuxx plus f of xt, and ux0 equal to f of x, u0t equal to h1t, and ult equal to h2t. And the similar thing you can do for non-homogeneous wave equation with non-homogeneous boundary condition and non-homogeneous initial condition. So, here first you need to truncate your problem into two part. Now, first you make your boundary condition a homogeneous boundary condition, then you truncate into two part. One part we have already solved, another part we solve with the help of Duhamel principle. So, here Duhamel principle plays a very important role in the sense that how to find out a solution of a non-homogeneous partial differential equation, means wave equation and heat equation, in terms of solution of homogeneous heat or wave equation. So, with this I end our lecture, and we will see some more example in our exercise assignment, and there we will get some more information about it. So, with this I end my lecture. Thank you very much for listening us. Thank you.